Now, differentiable means that the derivative exists. So our theorem says if f prime of A exists, then f is continuous at A. Okay, so this f prime exists part, that means that f is differentiable. F is, I abbreviate it as diffable. Okay? And a lot of times when we have an if-then statement, what we'll do is we'll use an arrow to indicate something we call an implication. So f is differentiable, that implies f is continuous. Okay, so this is a logical statement. And that's called, this logical statement is called an implication. And I want to talk about this a little bit because we want to talk about something else related to this. So when we write P implies Q, what this means is this means if P is true, then Q is true. All right. So what's a real life example? A real life example would be something like if it rains, then the ground is wet. So as an if-then statement, we're saying that it rains would be playing the role of P. The if-then statement is captured with the arrow, and then the ground is wet. This part here would be the Q part. So we have this idea of a converse, and converse isn't just the name of a sneaker brand. Converse actually in logic means we're reversing the direction of the arrow. So when you reverse the direction of the arrow, what does that look like? Well, reversing the arrow would basically mean that Q implies that P is true, right? So if we looked at our real life example, what would the converse be? The converse would be if the ground is wet, then it rained. Okay. Now, when we look at this statement that I've just written, this statement, if the ground is wet, then it rained, this is obviously false. There's plenty of reasons why the ground could be wet. Maybe someone washed their car, or, some other reason. Maybe there was flooding. Who knows? Maybe the snow melted. There could be many reasons why the ground is wet without it actually raining. Okay, so the converse is, even if the implication is true, the converse is not always true. So I guess I should mention that, the converse is not always true. So when both P implies Q and the converse Q implies P are both true, we write it like this. We write P and then we'll put a double arrow, a bidirectional arrow Q like this. And this means P if and only if Q. And that means P implies Q and Q implies P. So P implies Q is true, and Q implies P is also true. All right. So now let's go back to our original theorem. Our original theorem says if f is differentiable, this implies f is continuous. And then I want us to look at this true-false statement I have right here. So we're wondering, is it true or false that continuity implies differentiability? I'll give you a second to think about your answer to that. Okay, well, it turns out this is false. And how can I show you that it's false? I show you it's false by providing a counterexample. So the counterexample is the function f of x equal to absolute value of x. Okay, so how do we know that this does not have f of x equal to absolute value of x is not differentiable? First of all, we know it's continuous, right? I could draw a graph, and we know that the graph of absolute value, whoops, shaky hand, looks like that. So this is absolute value of x. And we can see that it's continuous because I could draw the whole thing without lifting my pen. We also know that I could write absolute value of x as a piecewise defined function. So this is going to be x if x is greater than or equal to 0, and is equal to negative x if x is less than 0. And then when I take the derivative of this, so let me call this function f of x, when I calculate what f prime of x looks like, what is that? When I take the derivative, I'm going to take the derivative of each of those pieces. So the derivative of x is just 1, and the derivative of negative x is negative 1. And it's really unclear what happens actually at the point 0. So we're going to put if x is greater than 0, and this is if x is less than 0. And when we go to graph f prime, the graph is going to look like this. So I probably should use the axes in black. And, here's 1, here's negative 1. I'll draw the graph in blue. I'll put an open circle at 0. This guy goes like this. Put an open circle at 0. This guy goes like this. In other words, when we come from the left side, the slope is negative 1. When you're on the right side of 0, the slope is 1, and that's represented by this graph right here. This is the graph of f prime of x. Okay, so I hope we can see that at 0, the derivative is undefined. You come from the left, it looks like it's negative 1. You come from the right, it looks like it's 1. What is it at 0? Who knows? So the derivative is undefined at 0. Derivative undefined at 0. Okay, so that's a counterexample. So continuity does not imply differentiability. And the reason I take some time to go over this is because this idea of an implication versus a if and only if statement is something that's kind of important for mathematics. So while we're on the topic of differentiability, let's take a look at the 3 ways that a function can fail to be differentiable. The first way is that you have a corner or a cusp in your graph. And that's really basically the situation that I just described with the absolute value. If you have something that looks like, a cusp is kind of a pointy thing, or a corner or something like that. The second way that it could fail to be differentiable is if you have a discontinuity. So, maybe you have some sort of jump discontinuity like this. Then, at the point A, it's not going to be differentiable. Okay, and then the third one is you have a vertical tangent line. That's basically saying, you know what, the derivative is infinity, and infinity is not a real number. So, maybe it looks something like, and then it kind of goes vertical for a little bit, and it goes like that. So then your A would be at that point where that vertical tangent line is achieved. Okay. The last thing we want to talk about is something called a higher order derivative. So a higher order derivative is just a derivative of a derivative. This thing is just a derivative of a derivative. Okay. So we have different notations for this. Let me tell you about the Leibniz notation first. Remember when we talked about the first derivative, we wrote it as dy dx. And then when you apply the differentiation operator, that means you're going to take a derivative. So if I apply the differentiation operator, I have a d dx like that. This is not the notation we use. This notation means take the derivative of the first derivative. The actual notation that we have looks like this. It's d squared y dx squared, like that. So it basically kind of looks like you're multiplying the d's together here, and you're multiplying these two dx's together, and that's how they cooked up this crazy Leibniz notation. Another way that we do it is we say, f prime of x, then f double prime of x, then f triple prime of x. For some reason, when we get higher than 3, we start to put the number of the derivative, so the fourth derivative, but we put that in parentheses, kind of as an exponent, or a superscript, I shouldn't say exponent. But this is what a higher order derivative looks like. We'll do a lot of examples in class together, okay? Take care, everyone.